Well, good day wherever you are. For logistical reasons, this talk is being recorded in August at my home in Canmore, Alberta. And from the living room, you would normally have a clear view of the Canadian Rocky Mountains. But because of this summer's wildfires in British Columbia and the northern US, our nearby mountains look more like what you see here. In winter, of course, the local scenery looks rather different, as documented in my wife's picture book of Canmore throughout the year. But to get down to business, analytical electron microscopy can have two slightly different meanings. Either electron microscopy combined with chemical analysis, or else microscopy with numbers, quantitative rather than qualitative. In reality, these two aspects often go together, as I'll try to illustrate in the talk. The subtitle here is a quotation from Otto von Bismarck, the soldier-statesman who in the 19th century united Germany into the Second Reich. He is reported to have described politics as the art of the possible, Realpolitik, and it seems to me that this description can also be applied to science, including electron microscopy. Often we are prevented from achieving what we would like for a variety of reasons, some practical and some fundamental. So I'd like to describe some of the limitations of AEM, as well as its considerable achievements over the last 70 years. Our ideas about the universe depend to a large extent on what we can see with our eyes. This slide shows a physicist's view of the human eye, which contains a lens system of variable focal length, which focuses incoming light onto the retina, with its rod and cone cells that transmit the image to the brain. Those receptor cells have a diameter of a few micrometers, and they contribute one limit to the image resolution. Other limits arise from aberrations of focusing and from diffraction of incoming light at the entrance pupil. Taken together, these three factors indicate that our optical system has an image resolution of about 6 microns. But to estimate the smallest object that we can resolve clearly, this image resolution needs to be multiplied by a ratio of the object and image distances, giving us an object resolution of around 75 microns, about the diameter of a human hair. To see anything smaller, we need a microscope, and the simplest kind consists of a single lens placed very close to the eye. In the 17th century, van Leeuwenhoek used the instrument you see here to reveal objects that had previously been invisible. Leeuwenhoek's microscope was very hard to use, so today we use a compound microscope with 2 eyepieces and built-in illumination. It can act as a transmission microscope if the object is thin and transparent, or a reflection microscope if we have an opaque object such as a metal. In either case, the glass lenses can be good enough to make aberrations unimportant, so the object resolution is limited only by diffraction. The Rayleigh formula then tells us that the resolution depends on the wavelength of the light and the numerical aperture of the objective lens. This numerical aperture can be made large enough that the spatial resolution ends up being close to the wavelength of the light, of the order of 500 nanometers. So an obvious way of improving the resolution is to reduce the wavelength. Soft X-rays have a wavelength of just a few nanometers. A zone plate can focus them and give us an object resolution of about 30 nanometers. Much better than the light microscope, but about 9 times the wavelength, reflecting the fact that the zone plate has aberrations. It is also an inefficient lens, so we need a bright X-ray source, such as an electron synchrotron. This is an enormous machine, and what you see here is just one beamline at the Canadian light source. Of course, 30 nanometers does not get us down to the atomic scale. For that, we need even shorter wavelength. In the 1930s, it was realized that electrons could be accelerated to form a beam, which could then be focused using magnetic fields. The electron wavelength depends on its speed, and for an accelerating potential of only 100 volts, de Broglie's formula predicts a wavelength of around 1/10 of a nanometer, the diameter of a hydrogen atom. If we use 80,000 volts, the wavelength is even shorter, about 4 picometers. This all sounds highly promising, but when the first commercial transmission electron microscope appeared in 1938, its resolution was 10 nanometers. This is about 50 atoms wide and over 2,000 times the electron wavelength. The reason, of course, was imperfect lenses. The magnetic fields used to focus the 80 kV electrons suffered from spherical aberration. The obvious solution was to build better lenses, and this was accomplished over the next several decades. Another thing that helped was to increase the accelerating voltage of the electrons from 60 or 80 kV up to 300 kilovolts. In that way, the TEM achieved atomic resolution, although this was still many times the electron wavelength, because it turns out that spherical aberration is unavoidable in an axially symmetric lens. In the 1970s, some scientists thought to go further and use millions of volts to accelerate the electrons. The French government funded a 1 million volt microscope in Toulouse that was housed in the spherical building that you see on the right, which came to be known locally as La Boule. There was even a 3 million volt microscope on the same site, but none of these instruments achieved atomic resolution because of the problems involved in stabilizing the high voltage. However, these huge microscopes could examine thicker specimens, which made them useful for some purposes. A practical way to achieve even higher resolution turned out to be the use of multipole aberration correctors, as shown here. These devices demand extreme accuracy of alignment, and it was not until the start of this century that the necessary computer control was developed, allowing the resolution of a TEM to reach a subatomic level. Nowadays, atomic resolution TEM images are commonplace. What you see usually are not single atoms, but atomic columns in crystals. And lens aberrations are not completely corrected. The resolution is typically 25 times the electron wavelength. But subatomic resolution allows materials scientists to see small displacements of atoms at defects such as grain boundaries. So electron microscopists are quite happy, except about the cost of these instruments, which now amounts to several $1 million. In fact, aberration correction is not essential for seeing atoms, as was shown in the 1970s by Albert Crew, who imaged heavy atoms that were dispersed on a thin carbon film. He used a scanning transmission electron microscope, which scans a finely focused probe of electrons across the specimen and records the image serially as a function of time. The resolution of an STEM is determined mainly by the electron probe diameter, which was several atoms wide in Crew's instrument, but small enough to resolve atoms when they are widely separated. Crew's design used a field emission electron source, whose small source diameter makes it easier to form a sub-nanometer probe. This kind of dedicated stem still exists, manufactured in Seattle by the Neon company. Nowadays, most conventional TEMs can also be operated in STEM mode, and some of them can achieve atomic resolution, as shown here. In fact, STEM has several advantages compared to fixed beam imaging. It provides images from particles that cannot be easily focused, such as electrons scattered through high angles, or secondary electrons, or X-ray photons. This makes it particularly suited to analytical microscopy, which often combines several different signals in order to extract physical and chemical information about a specimen. And the same scanning principle is used in the SEM, which is able to examine thick samples, but doesn't quite achieve atomic resolution. One holdout in transmission microscopy has been cryo-EM, where beam-sensitive specimens such as proteins can now be imaged with near-atomic resolution. These light element specimens require phase contrast imaging, which can be achieved in a conventional TEM just by defocusing the objective lens. However, procedures for extracting phase information from STEM images are being actively pursued. One big surprise in the 1980s occurred when IBM scientists showed that atomic resolution images could be achieved by scanning a sharp tip within 1 nanometer of a surface. This discovery resulted in commercial scanning tunneling and atomic force microscopes that are a fraction of the size of any electron microscope, and which looked at that time to be a serious challenge to electron microscopy. But although STM and AFM can produce impressive images from a variety of different signals, their atomic resolution is restricted to samples with very smooth surfaces. Also, these instruments cannot see very far below a surface, and they're not very useful for determining chemical properties. For that purpose, we need a signal that is strongly element-specific. The first attempt at elemental analysis with nanometer spatial resolution was made by Hillier and Baker using this electron beam instrument. It had an electron source at the bottom, 3 magnetic lenses to form an electron probe, and an electron spectrometer that formed an energy loss spectrum containing ionization edges whose energy is characteristic of individual elements. The original aim was to analyze with 20 nanometer spatial resolution, and this failed because of the poor vacuum and the resulting hydrocarbon contamination by the electron beam, a problem not that uncommon even today. But by defocusing the probe to 200 nanometers, Hillier and Baker were able to record ionization edges from various elements and to show the distribution of these elements within the thin specimen. It took another 50 years for electron energy loss spectroscopy to become an established elemental analysis technique using spectrometers manufactured by the Egerton company that could be attached to any TEM. Here on the right-hand side, you see the ionization edges that are characteristic of each element. Measurement of the intensities of these features gives a quantitative measurement of the elemental concentrations. This form of elemental analysis has been used increasingly by materials scientists and occasionally in biological work. Here's an example of its use in the semiconductor industry for investigating the manufacturing problems of integrated circuit chips. One indispensable tool for preparing the necessary thin specimens has been the focused ion beam machine, where a beam of gallium or other ions is used to thin down material within a region of interest, or to cut through material and produce a cross-sectional slice. On the left here are portions of the energy loss spectra recorded from different regions of a logic chip, showing the ionization edges of some of the elements present. On the right are STEM images formed from electrons whose energy loss corresponds to a particular edge, and which display the spatial distribution of that element. Such elemental maps allow the results of processing steps to be visualized and the diffusion of elements to be studied. The electron spectrometer has an energy resolution of the order of 1 eV, and sometimes better, sufficient to resolve spectral fine structure that can reveal the electronic or atomic structure of a specimen on a sub-nanometer scale. The example here involves amorphous carbon layers that are used as hard coatings on data recording disks and recording heads. The hardness derives from the presence of diamond-like sp3 bonding between some of the carbon atoms. But diamond is a metastable form of carbon, so there is usually also some graphitic sp2 bonding. EELS can measure the ratio between these two kinds of bond because carbon K-shell ionization edges, seen here on the left, exhibit a sharp pi-star peak when sp2 bonding is present. By quantifying the ratio between that peak and the subsequent broad peak, the fraction of diamond-like sp3 bonding is here plotted against distance through the carbon layer as the red curve on the right-hand side. These measurements required a cross-sectional specimen, which in this case was made by conventional thinning techniques, followed by argon ion milling, giving rise to the cross-sectional TEM image showed at the top right. Because this carbon layer is amorphous, the bonding type would not be easily measurable using electron diffraction. One limitation of EELS is that it requires a very thin specimen. Otherwise, the background to the characteristic features becomes too large. It's actually not the background itself that is troublesome, but the electronic noise present in the background. This makes analysis rather like trying to see the mountains through the fog. Fortunately, there is an alternative to electron spectroscopy, namely the spectroscopy of X-rays that are emitted when energetic electrons enter a solid specimen. In the 1960s, wavelength-dispersive spectrometers were added to a TEM, or an SEM, and there is still an instrument known as the Electron Probe Microanalyzer that uses WDX technology to measure elemental concentrations down to parts per million in favorable cases. The wavelength-dispersive spectrometer has good spectral resolution, but is inefficient because it has to scan through each X-ray wavelength in turn. If we want really good spatial resolution, the specimen must be thin, and WDX measurements then take a long time. A breakthrough came with the development of energy-dispersive X-ray spectroscopy, where a special form of silicon diode detector is used to generate an X-ray spectrum from a wide range of photon energies simultaneously. Data recording then became much faster and more efficient. The silicon diode had to be cooled to 100 degrees Kelvin, so a liquid nitrogen dewar became a prominent feature of any TEM used for analytical microscopy. Recently, silicon drift detectors have been introduced that don't need liquid nitrogen cooling and can energy analyze X-ray photons at higher rates. Advantages of using X-rays for analysis are that the specimen does not have to be quite as thin as for EELS, and there is very little background to the characteristic X-ray peaks. These peaks are Gaussian in shape, with a full width between 100 and 150 eV. However, that relatively poor energy resolution is only a major problem at low photon energies, where peaks from elements of low atomic number may overlap each other, or overlap with peaks from heavier elements. Usually, EELS is more sensitive and accurate for measuring elements of low atomic number, but improvements in EDX detectors have made light element detection possible. Here is an example of EDX analysis of a lithium alloy. Scanning an electron probe across the specimen allows the elemental concentrations to be displayed as elemental maps, and sophisticated software makes the measurements quantitative. Using a detector with a large collection angle, X-ray maps can now achieve atomic resolution without the statistical noise being overwhelming. Here you see STEM images of the atomic columns in single crystal strontium titanate, obtained using the characteristic strontium, titanium, and oxygen X-rays, and displayed in 3 different colors. In the top right image, the 3 colors have been superimposed, so that the strontium and titanium atomic columns can be separately identified. But note that the blue oxygen image is more uniform, a result of the spatial delocalization of the signal that I'll mention towards the end of the talk. As a result of these technical improvements, it's even possible to identify a single atom of many elements, using either EELS or EDX spectroscopy. The X-ray spectrum at the top was obtained by placing a 1.4 angstrom diameter STEM probe on a silicon atom for about 10 seconds. The sample was single-layer graphene, with silicon atoms occasionally substituting for carbon in the 2-dimensional lattice. You can see carbon and copper signals from the surrounding environment, but also a clear peak at about 1.8 keV that is characteristic of silicon. The X-ray and energy loss spectra at the bottom were recorded from a specimen containing erbium atoms, each enclosed within a C82 fullerene molecule. These molecules were in turn encased in a single-wall carbon nanotube to form a so-called p-pod structure. The purpose of the double encapsulation was to ensure that an erbium atom would remain long enough in the electron beam, about half a second, to give a visible erbium signal. Unfortunately, the 60 kilovolt electrons used to form a 1.5 angstrom probe are capable of displacing any atoms that are not strongly bounded to their surroundings, and putting the erbium atoms in a carbon cage minimizes this possibility of radiation damage. In the X-ray spectrum on the left, the large blue arrows identify M and L line peaks that are characteristic of erbium. The smaller arrows point to molybdenum or sulfur and chlorine peaks arising from stray electrons hitting the molybdenum support grid and from traces of the solvents used in the specimen preparation. In the energy loss spectrum on the right, an erbium atom is identified from its N-shell ionization edge, and of course there is a large carbon K edge arising from the fullerene and nanotube components of the specimen. Such results raise the question, has analytical electron microscopy already reached its ultimate goal of perfection? Well, I'm sure you're familiar with the idea that in a scientific paper you present your best results. And from what I said about specimen preparation, you might agree that conditions were chosen to be ideal for identifying single atoms. In the real world, nature is rarely so accommodating. Assuming that the main goal of electron microscopy is spatial resolution, we can ask how that quantity varies depending on several factors, the most important of which are listed here. One factor is obviously the instrumentation, quality of electron optics, of the electronics, and so on. In other words, engineering problems. But there are other considerations that are more fundamental because they arise from physical principles. I'd like to discuss each of these factors in turn to show how things stand today. In terms of instrument design, improvements in electron optics, including aberration correction, have led to spectacular performance. Improved electronics has also played a big role, including fast readout of spectra and images, which has actually relaxed the stability requirements for power supplies, which were starting to require expensive hand-picked components. But the performance of an electron microscope depends also on the environment in which it operates. It has long been known that low levels of AC magnetic field are needed for high-resolution TEM. Where this is not readily achievable, field sensing devices coupled to Helmholtz coils can be used to compensate for residual fields. Mechanical vibration must be low, and this is usually achieved by installing the instrument on a thick concrete slab, possibly with an anti-vibration mounting. Changes in air pressure can affect image stability because most TEMs use a side entry specimen holder that is vulnerable to pressure changes. At the top right here, you see a plastic enclosure being used to protect the specimen region of a TEM. Temperature changes must also be minimized, usually by using low airflow in the microscope room and water-cooled panels on the walls. It's now common to see expensive TEMs enclosed in a metal box, which probably helps to reduce several of the above problems. Despite all these precautions, there are some physical effects that can limit our object resolution, and one of these is called beam spreading or beam broadening. Our analytical signals are generated by inelastic scattering of the beam electrons, which involves very small scattering angles. But the structural information in TEM images comes mainly from elastic scattering, which involves deflection angles that are large enough to cause a focus beam to spread laterally as it moves through the specimen. This is a minor problem for EELS, where the specimen is very thin, but it can be appreciable for EDXS spectroscopy. It becomes a major limitation in an SEM, which uses a bulk specimen, and where beam spreading limits the spatial resolution of X-ray maps to some fraction of a micrometer. In the case of a thin amorphous specimen, it's easy to calculate the beam broadening at a particular plane by summing over the elastic scattering that occurred at previous planes. The resulting blue curve on the left shows the current density after a sub-nanometer beam of 100 kilovolt electrons has traveled 100 nanometer into a silicon specimen, plotted against distance from the center of the probe. At first sight, this doesn't look much different from the dashed red curve, which is the current density profile at the entrance surface, except for a small tail that extends to larger radius. But if we sum up the electrons that lie within a given radius, comparison of the blue and purple curves here shows that only 40% of the electrons lie within the original probe radius. The remaining 60% are distributed at distances up to at least 10 nanometers. This means that if we wanted to analyze a nanometer-sized precipitate that was located near the beam exit surface, 60% of our analytical signal would come from the surroundings, making quantitative analysis inaccurate. Things are not so bad in a crystalline sample, provided the electron beam coincides exactly with an atomic column and is parallel to it, the situation shown here on the left. The positively charged atomic nuclei actually focus electrons down the atomic column. But if the probe is shifted just half an interatomic distance, or is not parallel to a crystal axis, then we have the situation on the right, which is more like the amorphous case. The only way to avoid beam spreading is to make the specimen extremely thin, which is not always possible. A third factor affecting spatial resolution, particularly in EELS, is Coulomb delocalization. Our analytical signal is a result of the excitation of atomic electrons. They lie outside the nuclei of each atom and can be excited from some distance away by the Coulomb field of a beam electron. Another way of viewing this effect is as a consequence of the Heisenberg uncertainty principle. The small inelastic scattering angles now appear as a disadvantage because after scattering, the transverse momentum, delta P, is small, and the uncertainty in lateral position of the scattering event is therefore large. We can use the Rayleigh resolution formula to estimate the diameter containing 50% of the scattered electrons. The result is a simple formula that tells us that this diameter has atomic or subatomic dimensions for high energy losses, like the ionization edges used for elemental analysis. So atomic scale elemental analysis is possible by EELS or EDX spectroscopy. But the 50% diameter becomes a few nanometers or even tens of nanometers for the lower energy losses that are sometimes used for EELS structural studies. And reducing the specimen thickness has no effect on the Coulomb delocalization. This delocalization effect is best described by a point spread function, the blue curve shown here. And once again, the tails of this function mean that some of the analytical signal is generated at relatively large distances from the center of the electron probe. So if we try to represent delocalization by a single number, that number can vary by a few orders of magnitude, depending on what fraction of the signal we specify. A final factor that affects spatial resolution is the statistics of the signal that provides the structural or chemical information about a specimen. In many situations, our electrons insist on behaving as particles, and the scattering events that provide the information are subject to Poisson statistics. This is a situation familiar to biologists or anyone who conducts clinical trials or surveys of public opinion. To get a more accurate answer, you need to increase the size of the survey, which costs more money. But in the electron case, we run up against a more fundamental limit. If we use too many electrons to analyze a beam-sensitive specimen, they destroy the structure we are trying to measure because of radiation damage. So there is a maximum allowable electron dose, DC, that depends on the radiation sensitivity of the specimen, and the concept of dose-limited resolution takes this into account. The formula for DLR shows that it depends on the detective quantum efficiency of the electron detector and on the efficiency of our signal collection. It also helps if we have a specimen and an imaging or spectroscopy method that provides high contrast C between different regions of a specimen. That's why phase contrast is used for high-resolution imaging of organic specimens, and why a lot of effort has been put into increasing the collection efficiency of X-ray detectors. The remaining DLR factor is the radiation sensitivity of the specimen, represented inversely by its critical dose DC. If we expose a TEM specimen to electrons and form an image, the resolution starts off poor because we have few electrons and bad statistics. With increasing electron dose, the dose-limited resolution improves. but beyond a dose of the order of DC, the resolution starts to get worse again because radiation damage is destroying the original structure and reducing the image contrast. For most biological specimens, this dose-limited resolution is many nanometers, far worse than the electron-optical resolution of a TEM. For a metallic specimen, the situation is much better. The dose-limited resolution may have subatomic dimensions, and the actual resolution is limited by the electron optics. To understand the differences here, we need to briefly consider the mechanisms of beam-induced damage. If a beam electron passes within a few picometers of an atomic nucleus, it is elastically scattered through a large angle and can transfer enough energy to the nucleus to displace the atom and destroy the original atomic structure. This knock-on damage is most evident in electrically conducting specimens, but is rather slow because the probability of high-angle scattering is small. This slow damage can even be largely eliminated if we can reduce the accelerating voltage, and therefore the kinetic energy of the beam electrons, below some threshold value, such that the maximum energy transfer is less than the atom's binding energy. In non-conducting specimens, most of the damage arises from inelastic scattering. This process transfers energy to atomic electrons, breaking chemical bonds and generating secondary electrons that create even more damage. Together, these effects are known as ionization damage or radiolysis. For a beam-sensitive specimen, knock-on damage does occur, but is insignificant compared to radiolysis, so reducing the accelerating voltage has little effect. Instead, we can lower the specimen temperature, which generally reduces the rate of radiolysis. In cryo-EM of biological specimens, the specimen temperature is reduced to around 100 Kelvin, reducing radiolysis by typically a factor of 5 to 10. In addition, biomolecules or viruses are encapsulated in vitreous ice, which helps to keep the atoms in place by what is often called a cage effect. Thirdly, the images of thousands of molecules are combined by computer software, which increases the signal level or spreads the damage over many molecules. Using all three tricks, the dose-limited resolution is improved from several nanometers to something approaching atomic dimensions, allowing the structure of complex molecules to be determined. More recently, cryo-EM is proving useful for examining some sensitive inorganic specimens, such as lithium battery materials. For aqueous systems and living cells, chemicals known as scavengers have been used to reduce the effects of ionizing radiation, but this procedure does not seem effective for solid specimens in the TEM. Radiolysis is not quite instantaneous and can actually be outrun by recording diffraction patterns from the intense X-ray pulses produced by a free electron laser. But this involves something like 10 to the 12 photons within each 100 femtosecond pulse, and a similar trick is unlikely to work with electrons because of their Coulomb repulsion. However, radiation damage is a complex process and proceeds in stages. It might be possible to outrun some of the later stages by using a sufficiently intense electron beam and fast data readout. For example, the dose rate in a sub-nanometer STEM probe formed from a field emission source exceeds that of the latest X-ray synchrotrons. Another possibility is to use a pulsed electron beam, and there is some evidence suggesting that this might be effective. Is there anything else we can do? Well, how about persuading electrons to act more like waves than particles? That may sound idealistic, but it has given rise to an activity known as quantum electron microscopy, one variant of which is Multipass TEM. Suppose we want to use phase contrast TEM to image a light element specimen, using N electrons. A gated two-mirror device, shown schematically on the right, makes each electron pass m times through the sample before the electron is released and recorded in the image plane. This increases the phase signal by a factor of m, but also increases specimen damage by the same factor. However, we can avoid this extra damage by using m times fewer electrons, resulting in a multipass phase signal is the same as for n electrons passing through once. And since we used m times fewer electrons, the statistical uncertainty in the signal is reduced. Consequently, the shot noise, the signal-to-noise ratio, and the dose-limited resolution should all be improved by a factor of √m. The simulations at the bottom of the slide show how the image of a molecule ought to appear for the same dose and damage, but with different numbers of passes. From these simulated images, it looks as if m equals 12 or 16 would be optimum. As you might imagine, the engineering here is not trivial. Timing of the mirror should not be a big problem. It needs a few nanoseconds precision, but the electron wave must maintain coherence during the m passes. The equipment has been set up at Stanford University, and as far as I know, nobody has claimed success. However, this field is driven by apparent successes in light optics. The general aim is to reach the Heisenberg limit, where spatial resolution is limited by the photon or electron wavelength, rather than by the shot noise that represents particle properties. In conclusion, I've tried to show how analytical electron microscopy has advanced over the past 70 years. It is now a sophisticated and expensive activity, whose capabilities are starting to be limited by basic principles of physics and chemistry. To return briefly to Otto von Bismarck, another quotation attributed to him is, "Only a fool learns from his own mistakes. A wise man benefits from the mistakes of others." Applied to science, this might mean keep up with the literature, and also try to help future scientists by acknowledging your mistakes rather than allowing misleading data to remain uncorrected. The kind of thing I have in mind is what you see here. Our goal was to directly measure Coulomb delocalization by imaging a sub-nanometer STEM probe using inelastically scattered electrons. This seemed a good idea at the time, and aberration-corrected optics would make the anticipated effect measurable. The results were published as an M&M conference abstract, and they did not behave as expected. We ended up learning more about the instrumentation than about the physics. But the exercise did give us a better understanding of delocalization, so I decided it was worth publishing as a short note and as a warning to others. Well, this really is the end. Thank you for listening.